In this video, we'll talk about the Simplex method for general linear programs and the fundamental theorem of linear programming. Alright, so what's the motivation here? Previously, when we talked about the Simplex method, we always focused on LPs in the standard form. And in the standard form, you have the following problem. So you have maximize C transposed X subject to AX is equal to B and X is greater than or equal to 0. We saw that the non-negativity assumption typically makes a practical sense because it usually represents some physical quantities like the number of units produced and so on. But in some applications, actually, you may not need to require non-negativity and the variable may have a negative value. So in some cases, you may have X that is a real variable. So why did we use this non-negativity assumption then to start with? The reason for this is that it allows us to use methods like the Simplex method because having non-negativity assumption ensures that our LP, whenever it's feasible, it will have at least one extreme point. And recall that the Simplex method, the way it proceeds, it goes through the extreme points of the feasible set until it reaches the optimal one or concludes that the problem is unbounded. Alright, so the non-negativity is in fact a crucial assumption for the Simplex method to work. Okay, so now what do we do when we have the variables that are general and don't have to be non-negative? How do we use Simplex method for this? Here we apply a simple logic, so we essentially reduce the general case to this case that we already studied. So instead of considering a real variable, we are going to introduce some additional variables and we'll represent our real variable as a difference of two non-negative variables. And of course, we can always do this. So for example, if you take an arbitrary number, say you take -5, right? So you can represent -5 as a difference of 0 and 5, both of which are non-negative. And essentially, this is what we are going to do. So when we have a variable, say x1, that is real, then we are going to represent it as x1 is equal to x1 prime minus x1 2 prime, where both x1 prime and x1 2 prime are non-negative. And the meaning of these two variables, x1 prime and x2 prime, they're essentially the positive part of the number and the negative part of the number. So essentially, x1 prime is x1 plus, the positive part of the number, and x1 2 prime is x1 minus, which is the negative part of the number. And what's the positive part of the number? This is the maximum of the number and 0. So if a number is greater than 0, then the positive part of the number is the number itself. If a number is less than 0, then it is 0. And the negative part of the number would be the maximum of 0 and negative x1. Okay, so whenever the number is negative, then the negative part of that number will essentially be the absolute value of that number. And if the number is positive, then the negative part of this number is 0. And even though the same number can be represented as the difference of different pairs of numbers, for example, -5, we saw that it can be represented as 0 minus 5, but I could also represent it as 1 minus 6, for example. But we will show that within the Simplex method framework, one of these two variables will always be 0, meaning that at most one of them can be positive, and therefore this meaning that we are talking about here will always hold within the Simplex method framework. Now that we know how to treat the unrestricted and signed variables in order to apply Simplex, we can actually claim that we can solve any LP using the Simplex method. Because look here, this formulation becomes very general For example, here I have maximize C transpose times X. What are the other possibilities for the objective? I could have, let's say, minimize C transpose times X, right? If I have a minimization problem, it is equivalent to maximizing the negative of C transposed X, all right? If this is Z here, then this is negative Z, and maximizing negative Z is the same thing as minimizing Z, but of course in the end we'll obtain the maximum value of negative Z, and we'll need to multiply it by -1 in order to obtain the optimal objective value for the minimization counterpart, right? So the objective covers all the possibilities. Then for the constraints, we have the equality constraints in the standard form representation, but then again it covers all the cases, because we saw that whenever I have a less than or equal to type constraint, I introduce a slack variable, so we add some slack variable, and whenever we have a greater than or equal to constraint, we subtract an excess variable. And this converts both of these cases to equal type constraints. This means that now any LP can be put in this form, and we can apply the simplex method to any linear program. Let's look at an example again of an LP that has all kinds of variables. So we have both unrestricted and signed variables, and we have non-negative variables here. And we have x1 is a real variable, and x2 and x3 are non-negative. So how do we convert this LP to the standard form? So here is our problem now in the standard form, and we can use the same techniques to convert any arbitrary LP to the standard form. So now let's see what is happening to these variables that we just introduced for an unrestricted and signed variable. So here is another example. So this just looks at an arbitrary tableau of some LP where x2 variable is unrestricted and signed. So we used x2 prime and x2 2 prime in place of x2. And of course, when we introduce x2 prime and x2 2 prime, they're gonna come with the opposite signs in all the equations. So here, for example, x2 in row 0 had the coefficient of 4. This means that x2 prime will also have the coefficient of 4, and x2 2 prime will have the coefficient of -4. Similarly, in row 1, x2 had the coefficient of -1, and the same coefficient will still be there for x2 prime, but for x2 2 prime it will be the negative of that coefficient. And this situation will be observed in every row of the simplex tableau. And because of the way we do the simplex iterations, we apply the elementary row operations, and exactly the same operations will be applied to both of these coefficients. And because this relation between the coefficients of these two variables, one is the negative of the other, is true for all the rows, when we perform elementary row operations, this relation will persist throughout the iterations of the simplex method. For example, if we do a simplex iteration here, this row wins the ratio test, x1 is the entering variable, we do the pivot, and we can see that the coefficients for x2 prime and x2 2 prime are always the negatives of each other in all the rows of the simplex tableau. So, and what this means is that x2 prime and x2 2 prime can never be both basic variables. If one of them is basic, like x2 2 prime in this tableau here, so we can see that it is a basic variable, right? But once you have 1 in this entry here, you will have -1 in the same entry for x2 prime. Right, so because one is always the negative of the other, which means that this variable cannot be basic at the same time. So therefore, at most one of them can be basic at any iteration of the simplex method, which means that at least one of them will be set to 0 at every iteration of the simplex method, and this implies that in fact x2 prime is equal to the positive part of x2, and x2 2 prime is equal to the negative part of x2, just like we discussed before. So within these simplex iterations, this is what we're gonna get. You will never have a situation when both of them are positive in any basic feasible solution. I want to conclude the discussion of the simplex method by mentioning the fundamental theorem of linear programming. In fact, we can prove the fundamental theorem of LP using the simplex algorithm. Essentially, you can see the statement of the fundamental theorem of LP by analyzing the steps of the two-phase simplex method and by looking at what can potentially happen with the LP when you apply the two-phase simplex method. So let's first look at the statement, okay? Every LP has the following properties. First, if it has no optimal solution, then it is either infeasible or unbounded. The way we classified LPs before was we said, okay, LP can be either feasible or infeasible, right? Then if it is feasible, it can be either optimal or unbounded. We also further subdivided the optimal case into two subcases where you have unique optimum and then you have infinitely many optima, right? Now what the theorem states here is that if LP has no optimal solution, then it is either infeasible or unbounded, which we can see from our classification, right? So, but again, we base this classification on our intuition, but to prove it, we need some more rigorous arguments. So why is this statement correct? Let's see what happens when we apply the two-phase simplex method. So we can formulate any LP in the standard form, right? So once we formulate it in the standard form, we can always start phase 1 of the simplex method, okay? And when we run the phase 1 of the simplex method, it will output that the problem is either infeasible or feasible. So for phase 1, we have either feasible or infeasible, right? Next, if it is feasible, we already analyzed the iterations of the simplex method. Then we saw that whenever we cannot pick the entering variable, it means that we found the optimal solution. If we can pick the entering variable and we cannot pick the leaving variable, then the problem is unbounded. And the only way we wouldn't terminate would result in cycling, and we know how to avoid cycling. Let's say we can apply the blends rule, right? So as a result, these are the only two possibilities once LP is feasible. And the feasible case is analyzed using phase 2, by the way. So by analyzing the two-phase simplex, we see that the first statement is correct, right? Next, second, if a linear program has a feasible solution, then it has a standard form representation in which it has a basic feasible solution. So this essentially follows from phase 1 of the two-phase simplex method, because we saw that by solving the auxiliary problem, we will obtain the optimal objective value of 0 for the auxiliary problem if and only if the original LP is feasible, right? And then once you find the optimal solution for phase 1, you actually have a basic feasible solution for the original LP, right? So we just drop the columns corresponding to the artificial variables and we obtain the standard form representation in which we have this basic feasible solution. Essentially, the whole point of the first phase of the simplex method is to provide the initial starting basis for phase 2 whenever the problem is feasible. And finally, the last statement here in the fundamental theorem of LP is that if the LP has an optimal solution, then it has a standard form representation in which it has a basic optimal solution. Again, if you look at phase 2 of the two-phase simplex method, whenever the LP is feasible and whenever it is optimal, we are going to find the optimal solution to this LP using the second phase of the two-phase simplex method, and that solution is going to be a basic feasible solution for our problem, so it's going to be a basic optimal solution. So we see that the simplex method is not only useful for solving LPs, but you can also use the analysis of this algorithm in order to establish some fundamental properties of linear programming in general, and not just with respect to the simplex method. Finally, I want to say a few words about the complexity of the simplex method and linear programming in general. So one of the homework problems you got was the so-called Kleminti LP. And you are probably wondering why you got this problem where you have to do like 8 steps of the simplex method. The purpose of this exercise was to show that there are examples where the simplex method has to visit essentially all the extreme points of the feasible region before reaching the optimal solution. So we start with the origin point in this case, and then we proceed to point B, then from B we go to C, then to D, E, and we go in alphabetical order essentially. Alright, so and finally we reach the point H. So we see that there are 8 corner points for this feasible region in 3D, and we visit every single one of them. Now 8 is 2 to the power 3. In general, Kleminti example can be considered in n-dimensional space, and then you will have 2 to the power n extreme points, and you are going to visit every single one of them just like it is done in 3-dimensional case. So the point of this example is to show that the simplex method can be extremely inefficient, because we could essentially just enumerate every single corner and pick the best extreme point instead of going through all the simplex iterations. And of course this example was constructed specifically to show that not always simplex method works great. In the worst case, it can take an exponential number of steps with respect to the problem size. The question of whether we can develop an efficient algorithm for linear programming for which there is no example where it would have to run in exponential time was open for several decades, and it was finally answered positively in 1980s when 2 different methods were developed for solving linear programs efficiently. The first one was the ellipsoid method, and the second one was the interior point method. Both are actually based on nonlinear optimization techniques, and the ellipsoid method is the first theoretically efficient method for linear programming. So it's efficient theoretically, but its practical performance tends to be inferior to that of the simplex method. But the interior point methods are known for both theoretical and practical efficiency, and the interior point methods are an integral part of the modern optimization software packages. So the solvers that you use in the class, they have both interior point methods and variants of the simplex method implemented. These are currently state-of-the-art techniques for solving linear programming. These methods are outside of the scope of this course, but our department does offer courses that discuss these methods in more detail.